Hello, my name is Takeru Aoki from the University of Electro-Communications. Today I will be talking about double-layered cortical learning algorithm for time series prediction. Cortical learning algorithm (CLA) is a time series prediction algorithm based on neural cortex. The human neural cortex has a multi-layer structure, whilst the conventional CLA has a single layer. To improve the prediction accuracy, this work proposes a multi-layer structure into CLA. Artificial neural network (ANN) is a well-known architecture based on neurons. This table compares ANN and CLA. Basically, ANN does not have synapses in the same layer. On the other hand, CLA has synapses in the same layer, and they work for the data prediction. In the viewpoint of input data, ANN receives a sum of weighted value, which is a continuous real value. On the other hand, CLA receives a bit set, which is a discrete value. For learning, NN increases or decreases continuous weight values. On the other hand, CLA discretely connect and disconnect synapses. Thus, they use the same concepts in different ways. Actually, CLA neuron model is more similar to biological ones than NN. This is the conventional single-layer CLA. It has cells, columns involving a set of cells, and a region which is the whole set of columns. CLA converts the time series data at T to binary data bits and inputs them to the region. Similarly, we repeatedly input the next input data at T plus 1 to the region. In each time step T, spatial pooling represents an input data by an active column pattern. Each column has two states, normal and active. In the spatial pooling, we select active columns from ones with many connected synapses to a data bit of 1. In this case, columns 3 and 4 has 2 connected synapses to data bits of 1, and they become active like this. Thus, the input data is represented by active columns. Also, CLA emphasizes a synapse strength of active columns, like this. In this way, CLA learns relation between input data bits and columns. Next, temporal pooling represents input data context by active cells. Each cell has 3 states: normal, active, and predictive. Predictive cells at the previous time step in active columns become active, like this. Thus, the data context is represented by active cells. Also, temporal pooling represents next input data context by predictive cells. cells with more than NAR connected synapses to active cells become predictive states. NAR is the threshold to make cells the predictive state. In this example, we assume that the two cells R23 and R32 has more than NAR connected synapses to active cells. They then become the predictive cells. In this way, the threshold NAR is the key to make the predictive states of cells. The setting of NAR has an impact on the time series prediction. When predictive cells become active cells in the next time step t plus 1, their synapses that made these cells predictive are emphasized. In this case, these predictive cells are involved in active columns at the next time step t plus 1. They then become active like this. Also, their synapses that made these cells predictive are emphasized. In this work, we propose a multi-layered CLA. This figure shows a two-layered CLA. They are respectively the first and second layers. They are associated with synapses. First layer selects active columns and cells as is the conventional CLA. Then, second layer represents active cells in the first layer by active columns. Also, second layer internally selects predictive cells in second layer. Then, second layer provides the feedback to first layer to assist prediction in first layer. We propose feedback methods in this work. This is the first layer and this is the second layer. In the first layer, they are active cells and they are predicted by the second layer. Then, feedback method relaxes the condition to make cells the predictive state in the first layer. Concretely, the proposed double-layered CLA reduces the number of cell synapses NAR connected to active cells to be the predictive state. The proposed double-layered CLA employs the number of cell synapses alpha point NAR connected to active cells for cells predicted from the second layer, such as cells. For other cells not predicted from the second layer, the conventional NAR is used. This helps to make cells predicted from the second layer, the predictive state in the first layer, even if the cells do not have more than NAR connected cell synapses to active cells. To verify the effectiveness of the proposed CLA, we compare the conventional CLA, the simple CLA, the proposed CLA and 3 RNN-based LSTMs using ADAM RMS prop SCD feature network optimization algorithms. This table shows parameters used in this experiment. As a metric to assess the prediction accuracy, we use the prediction error, which is the difference between the predicted value and the true value. This figure shows the total prediction error of the proposed double-layered CLA on the combined sign in the last half of the entire time steps when we vary the reaction parameter. Alpha equal 1 indicates that any prediction in the second layer does not reflect to the first layer. As a reference, the results of the conventional single-layered CLA is plotted as a horizontal dot line in this figure. From the results, we see that the total prediction error decreases by decreasing from 1. We see that there is the best parameter minimizing the total prediction error. In this case, alpha asterisk equals 0.25. Further decrease of alpha from alpha asterisk increases the prediction error since the influence from the second layer becomes too strong for the first layer. In the following experiments, we use alpha asterisk equals 0.25 for the proposed double-layered CLA. First, we use this sine wave. This figure shows the prediction error histories by 6 methods on the sine wave. These values are ratio of the total error to the conventional CLA. From the result, we see that the prediction errors of the 3 CLAs are lower than those of the 3 LSTMs. In addition, we see that the simple CLA and the proposed CLA achieves lower prediction errors than the conventional CLA. On the other hand, we cannot see a clear difference between the simple single-layered CLA and the proposed double-layered CLA. However, we see that the proposed double-layered CLA suppresses the cyclic increase of the prediction errors on sine wave. This result reveals that the proposed double-layered CLA improves the prediction stability. Next, we use this combined sine wave. This figure shows the prediction error histories by 6 methods on the combined sine wave. These values are ratio of the total error to the conventional CLA. From the results, we see a similar tendency shown in the previous slide on sine wave. That is, we see that the prediction errors of LSTMs are higher than CLAs. We also see that the proposed double-layered CLA significantly decreases the prediction errors compared with the conventional single-layered CLAs. Next, we use this combined sine wave. This figure shows the prediction error histories by 6 methods on the combined sine wave. These values are ratio of the total error to the conventional CLA. As the same with the previous two input datas, CLAs achieve better than LSTMs. We see that the proposed double-layered CLA and the simple CLA show similar histories, but the proposed method achieves lower prediction errors after 20,000 time steps. Next, we use this combined sine wave. This figure shows the prediction error histories by 6 methods on the combined sine wave. These values are ratio of the total error to the conventional CLA. From the result, we see that the proposed double-layered CLA achieves lower prediction errors than the conventional single-layered CLAs and LSTMs. Next, we use this combined sine wave. This figure shows the prediction error histories by 6 methods on the combined sine wave. These values are ratio of the total error to the conventional CLA. We see that the proposed double-layered CLA achieves better prediction accuracy than the conventional single-layer CLAs and LSTMs. Next, we use this logistic mapping. This figure shows the prediction error histories by 6 methods on the logistic mapping. These values are ratio of the total error to the conventional CLA. Also, in this case, we see a tendency that the proposed double-layered CLA achieves lower prediction errors than the conventional single-layered CLAs and LSTMs. These results reveal that the double-layered CLA improves the prediction accuracy compared with the conventional single-layered CLA by accumulating the predictors of CLA and interacting between them based on the proposed interaction mechanism. Finally, let me conclude my talk. To improve the time series data prediction accuracy, we proposed a multi-layered CLA. We proposed the mechanism to reflect the higher layer prediction to the prediction in the lower layer in CLA to assist the time series prediction. As a result, we showed that the proposed double-layered CLA achieves lower prediction errors than the conventional single-layered CLAs and ASTMs. As future work, we will accumulate more layers as multi-layered CLA and check the abstract data representation and prediction in the higher layers. In addition, to solve the problem that proposed CLA has more parameters than conventional CLA, we will consider the method of dynamic parameter setting. That's all. Thank you for your kind attention.